Hi everybody, I said my name's Peter from Eurag Research, and we're the lead partner on the MOOC that we've just seen. And yeah, it's a great introduction to this session, I think, because it starts at the basics. It's for everybody who wants to learn something about Earth observation cloud platforms, about data cubes, about data discovery, and about open science. So it's a great place to get everybody on the same page. Somehow here, just very brief, I also didn't prepare any slides, so it will all be live. Some brief information. So the general information actually is already given to you by Anka. And we're going to look into now the EO College platform. This is where the MOOC is hosted. So if you're a teacher or you want to participate yourself in the MOOC, that's the place where you will go to, where you have all the lectures rendered, where you have the videos and all the interactive content and the quizzes. Then we will show you a sample exercise. So the course is not only theoretical, but there's also exercises that you will carry out. They forward you to a hosted Jupyter environment from EOX. They have prepared this very nicely, and we have an integrated approach there together with EO College and EOX, trying to create the least friction while switching from one website to the next. Then we will carry out one of these exercises and have a look at how they function. And then I'll give a quick overview of the GitHub repository that we have. Because the course, it doesn't only talk about open science, let's say, it is completely open, and everybody who wants to contribute to it is invited to do so. And yeah, all the material is openly available. If anybody of you wants to, oh no, this wasn't good. If anybody of you wants to go along with me in this lecture, I invite you to also go to eocollege.org/courses/cubes and clouds. To get to look at the first sample lessons, you don't have to register. If you want to be forwarded to do the exercises, you should register, because then you will go into a hosted Jupyter Lab environment from EOX's set, and there you need a username and an account. So, but you can do that in the meanwhile. I think while I talk, you can just click on, probably when you go there, there will be a register button here, and you can just register. Okay, so let's start. So what is this course about? As said, it's about data cubes, cloud platforms, and open science. There's also a trailer that we've watched in the beginning already, so everybody who was here on time got to see a little bit of this cartoon. I advise you to watch it. It's really helpful, and it explains also to novices what we're generally doing in EO and cloud platforms. So not only relevant for this course, it's relevant, I think, for the whole field. If you want to explain it to your aunt or somebody, that's a great resource. So who is the course for? It's for people that finish geography, Earth observation science, geoinformatics, or for people that do data science and come a little bit closer to the Earth observation domain. So these are the two groups of people that we will have in mind. What we're going to learn, I think we've talked about that enough. Maybe one specific thing that you will be able to do after you finish this course, you will be able to create a workflow in a cloud platform and generate results of your own, and also be able to make these results open and share them. So it doesn't stop at creating results or whatever, so you will also really learn how to share them, and you make them publicly available and visible, and can show them once you go to your future employer or whatever. You go to a map and show, look, this little thing, this little tile here, I've calculated it, this is a stack item, this has the correct metadata, it has a license. Here you see the processing graph, so I really know what I'm talking about. So that's the idea behind the course. That's not yet in place, but will be soon in place. What we will look in today are, so here you see the different chapters of the course. So what is a cloud platform? What is a data cube? What is open science? These are very theoretical to get everybody on the same base. Then you will start with data discovery. So where do you find data? What kind of data do you find? And finally, how do you access the data? And this is what we're going to look at now. Then we have one on data formats and performance with the emerging cloud-native data formats and so on. And finally, the last part of the course is very applied. That's the one where you learn how to create a whole workflow. In this case, it's the NDSI for generating a snow map and comparing it to runoff data with openly available data. The next one will be how to validate your results. And the final one will be how to share your results. And for now, we're going to look into a sample lesson. So this is what you will see once you're logged into the course. You will have some lesson content. For example, here we're talking about data access on data cubes. So here you see the different chapters. We have what is a filter operation, what is an apply operation, what is a reduce operation, what is a resample, aggregate, and so on. Oh, that's unfortunate. I have a couple of these open, so we can continue. For example, here, just imagine that I have clicked on reduce. Then you will find, I think, maybe some of you know extremely well what reduce is on a data cube. Some of you probably don't know, so that's why it's good to have an explanation for it. And this material is kindly reused from OpenEO. I think Matthias was also largely involved in creating it. But that's the good thing about open science, let's say, that it is open and it is reusable and it's there to be put into a different context. So we explain what a reduce operation does on a data cube. Once you have read this, you will find this exercise button. And you can click on it, and I hope that this works. Looks good so far. And you're forwarded to a hosted Jupyter Hub environment, so you can directly start coding on this notebook that is made available for you. I click OK, and it should appear somewhere here. Yeah, here it opens. You have the according kernel, and then you have the integrated notebook available here. All the libraries you need are already pre-installed, and you can just start reading through what is going to happen. In this example, we say, okay, we're using the process reduced dimension. We also explained that here we are not connecting actively to a backend, so that is what we explained in the first chapter, what's a cloud platform, what are backends, and so on. We're using the client-side processing of OpenEO, which is ideal for prototyping and doing these small-scale exercises. We explain a little bit this concept, and then you can directly start running the notebook. Let's see, yeah, at some certain points during the, this doesn't matter though, it's still running. At some certain points during the notebook, okay, now you see that you load your data from a stack catalog, which is an openly available one from element 84. So you load this data and you do a reduced dimension operation on it, which is, in this case, you take the minimum over the time dimension, so you can also look into this interactively so that students understand what is actually happening here. You take the minimum, and then you execute. And you will get the data in your workspace then, so you can have a look at it, and then you can see, so what has happened, what is the data cube that I'm actually getting. So here you can count the numbers of dimensions, which dimensions does it have. You see it doesn't have a time dimension anymore. So that is what happened during the reduce operation. You got rid of the time dimension and you took the minimum a long time. So this is how the course will go on and explains you what each process does to a data cube, and at some points you will find this quiz hint. Look carefully at the number of pixels of the loaded data cube, so we can still continue doing some operations. So now we're reducing the band operation and taking a mean over the bands. And we're executing it. And then later on in the quiz, you will have to know how many pixels does this data cube have in total, let's say. So that is how we link the exercises to the quiz. So this would be 21 times 1405 times 713. And this is one information that the student has to figure out himself and then to put into the quiz, which you would find, for example, here.
I don't know, but your college website is not loading. The same one?
Same problem for everyone. Jonas is not here, I guess. No. From DLR, Eberle. Yeah. Okay, then no. His boss. Okay, then let's hope. That's why I opened some of them. I think they just changed server to a more performant one.
It works on mobile.
Okay, yeah. Yeah, but I think they are aware of this, that it's not currently not in the best condition, but they will have to solve it. Okay, so maybe I have the quiz open that we can look at the quiz. No, the quiz I don't have, but we have the recap of the processes, for example. So this is, then let's say, the interactive elements of the course. So once they went through all this, they learned what the different processes are. Then you have to figure out, first you have to name, oh look, filter, I can at least find these processes, so they get to know them very well. Then the same thing here, explain what is a process that changes the resolution of a data cube's dimension. So then you have to think and figure it out and solve the crossword puzzle. And then finally here you have some interactive slides where you look at the image and you try to guess the answer. This process changes the number of dimensions in a data cube. So this should be reduce as well. Okay, and this is how you go through a part of the quizzes. There are then more quizzes later on that I guess I cannot access currently.
You want me to make a hotspot for you?
No, it's fine. Thanks. I think we have covered. Oh, yeah. Anyway, I think we've covered the whole round trip, so that is actually what we wanted to show you. If you have, unfortunately the quiz is not working, everything else was working fine. So maybe the GitHub repository, that would make sense. So here's the GitHub repository. You can read up everything on the course. You find all these notebooks that we were looking in. You can find all of these notebooks in the exercises folder of the lectures. You will find all the written content that we've looked at. You will also find it as markdown files here. So if you have another usage, as we did with the content we have taken from the OpenEO documentation page, you can also reuse this. So you can find all of the whole content here as markdown with the CC BY 4.0 license on it. And it will be available on Zenodo as well as a packaged course. So that's where we're currently at. And as said, it will start. We're currently migrating all of these markdown files into EO College. The connection to the exercises is built. So in January, we will be ready to open the course completely. And hopefully before December, we will have some test runs. And whoever is interested in doing a test run, just write us, get in touch. I think all of our contacts are there. And thanks for the attention. Thank you.
So, I'm going to run through a few slides introducing the DPSDL platform and how we can use this to run reproducible workflows in the cloud with Python and Jupyter notebooks. And then after I've dashed through that, anyone who gave us the GitHub login before the session will be able to log in with me and join in and step through a notebook and perform a simple workflow with JupyterLab and Xcube. So just to introduce DPSDL, I don't know how many have heard of it, but it's a platform for serving scientific exploitation needs and supports the science clusters, and there's a strong emphasis on teamwork, shared workspaces, sharing data and workflows. There are a lot of Jupyter hubs around, so it's frequently useful to mention what differentiates yes, teamwork and also a sort of out-of-the-box, ready-to-go data sets, which I'll elaborate on in the next slide, which is the exciting block diagram that every presentation like this has. So the main selling points are integration of scientific results. This is the data cube selling point is always combining different data sources, and we're trying to get that effort out of the way to let users concentrate on the actual scientific part rather than rather than fiddling around with data sources and with data formats. Collaborative and reproducible research. The reproducibility is, in our case, really notebook focused on the notebook that acts as a sort of development playground, and you can then export. You can export as a Jupyter book, as a saved notebook. You can encapsulate your data sources if you're not sure that the original source of the data is going to be around forever, and it's really a nice way to combine interactivity with reproducibility. So going into the overview, I promise I will not talk about every box in this slide. Mainly from the user side, these are the interesting bits. And this is the bit that you spend a lot of time looking at. This is the Jupyter Notebook service, very much like the one we just saw. The Xcube framework that we incorporate also has catalog and visualization features. I'll show the visualizer very briefly later on. It's an interactive web viewer that just gives a slightly more user-friendly view on your data sets than you can generally get in the little sort of pop-up cell in the Jupyter Notebooks. Then there are various other things, REST APIs for anyone who wants to interface their own modules, shared workspaces with the teams, data cubes. This is a sort of Xcube capability to massage various data sources into a data cube and let you combine them as easily as possible. And the Xcube server, which offers various APIs. This is more an advanced user thing if you really have, some standard interface that you'd like to interface over. There are increasing numbers of these implemented in Xcube. GeoDB is a geospatial database, which I won't go into because this is meant to be a 10-minute presentation. So looking at the data sources down here, Xcube has this uniform internal API for creating what we call data stores, and this produces this uniform user-facing interface for accessing quite a wide diversity of either bespoke project data, standard data stores from Copernicus, CCI, CLMS. Obviously, we have a generic S3 data store for accessing object storage buckets, so it's really a sort of, the idea is taking this big diversity and presenting it over a common interface so that it's the programmers who have to worry about how to actually get into all those diverse and occasionally quite interesting interfaces. The reproducibility angle comes in quite strongly here. With the project publication, you can export a Jupyter book. I mean, even a notebook on its own is quite reproducible as long as you stick it on Zenodo or something and freeze it in ASPIC. You can, of course, save your own data sets into object storage, export them, archive them. And so this is where the sort of publishable frozen outputs come out of the dynamic development process here. Up there is more the management stuff, and up there is the publication stuff, which I won't go too deeply into. So going a bit further into some of the things that came up on that block diagram. The core services I mentioned is the Jupyter Hub with the pre-configured user-defined Python environments. Again, it's the sort of the value proposition is in part here that a lot is pre-configured, preloaded, the software's there, the data sources are there, so you're not starting from a sort of raw Jupyter install, but you've got this sort of focused collection of data and software for the workflows that are of interest here. Reproducible workflows is Jupyter Notebooks I mentioned. There's a sort of flexible provision of cloud computing resources, GPU cores available for machine learning workflows. And I should differentiate here between the two parts of the data offering, the sort of pre-digested and presented analysis-ready data cubes, which are designed to support common use cases, and these are already sitting in DPSTL's own object storage, very straightforward to access. And then the virtual remote data cubes, which were in these remote stores in the previous slide. These are ones that open up instantly, but it's in your notebook, but of course it's actually a lazily backed store, so you can play around with these data cubes and the data only gets piped in from the back end at the point where it's actually needed. That's a quick view of the catalog. This is basically a friendly web interface with maps and metadata, and you can browse around, find your data set of interest, and amongst other things, it gives you a nice, neat Python snippet that you can paste straight into your Jupyter notebook to get at that, get at whatever data set you're interested in. Going a bit further briefly into the data stores, there are quite a few, and we keep making more. They're surprisingly easy to bang out once you've figured out the API. So we have the CCI Open Data Portal, the Copernicus Climate Data Store, the Marine Service, the Sentinel Hub Store, Xcube SMOS is under development. There's some standard OGC coverages store under development, so if this really takes off as an API as OGC are hoping, then that will be automatic import to the system for anything that supports that API. We also have Stack, which is, I mean, that really is taking off. And under development, we have a store that should be able to present any data cube-like online Stack data set as an instantly available Xcube data set within the platform. So this is a screenshot of the viewer. I'll briefly show that live in a moment. This gives you a map view, very nicely configurable, custom color maps and so on, and also time series analysis at points or across areas, and a few sort of in-development features like 3D views, which I won't present today, but that's currently being integrated and tested into the viewer. Oh, yes, I'm glad that was there to remind me. So yeah, there's also Dask available as a service for really heavy data processing. What you get to actually drive your notebook is, of course, a relatively modest amount of hardware. So, but then if you really have big data to process, you can get an on-demand Dask cluster, which spins up in the cloud and exists for exactly as long as it needs to process whatever volume of data you need to throw at it. AI, we have various AI libraries supported. I'm not going to talk very much about this at all because it's not the main focus today, but essentially this builds on the standard Python scientific stack that we're using in the rest of the system, PyTorch, MLflow, TensorBoard. So this is, again, focused on the reproducibility type aspect, this MLflow manager. It's sort of, I think the slogan is GitHub for your machine learning flows, but essentially trying to make everything a little more systematic and reproducible. And again, this is integrated into the shared team workspaces. So that serves those goals as well. This is fresh news from last week. It's that DPSDL is now available through the network of resources. So if anyone is interested, ESA is offering sponsorships for this, and you can go in there. I'm sorry about the extremely long and complex link there, but I think if you go into the network of resources site, it's possible to search for DPSDL and get to it fairly easily. So here's the introduction to the demo, but before I dive into that, I'll just do a quick live demo of the viewer because it's quite pretty and fun to play with. So here it's, oh, that's interesting. There should be something showing up there, but let's just, what shall we have? Let's try some permafrost. Okay, so the data set gets dynamically loaded in from a backend Xcube server. In this case, I think it's talking to a S3 object store. It's one of the pre-processed analysis-ready data sets. As you can see, we don't have a huge range of values here. We can play around with the scale to make them a little more visible. And another thing we can do here is, for instance, pick an area of interest, draw a polygon that we're interested in on the map, and then we get a time series calculated on the fly in that polygon. The analysis-ready dataset I'm about to show you in the demo is actually the ESA CCI land cover. So here it's also got a custom color map. This is the official land cover color map. So I'll just give a preview of the area that we're actually going to be looking at there. I seem to be halfway into a polygon here, never mind. So the demo is going to cover this area, the coasts of the Baltic Sea, of the Gulf of Bothnia essentially, along Finland and Sweden here, and we're going to look at some land cover differences. So you can sort of see in advance here what we're going to see is a sort of mixture of cropland and forest, and we're going to mix that up with some snow cover data and demonstrate a bit of masking.
So can we ask questions?
Certainly, yeah.
Where is this data stored now?
So this data set is cached on DPSDL's own object storage. I mean, yeah.
So are they geotips?
This has been processed into a multi-level ZAR. So yeah, but ZAR doesn't support pyramids yet, but within that's, I think, under discussion in some working group. But within the Xcube framework, we've already essentially developed a very simple ZAR-based pyramid, which is, well, it's more or less a sort of super directory of a ZAR containing ZARs at different resolutions, and that's, among other things, very useful for the Xcube viewer, of course. But yeah, we're going to see this ZAR up close and personal in the, and at this point, anyone who has signed up and is following along can, yes, I should have sent a link out, shouldn't I? Because now everyone's got to type this in. Sorry about that. Yes, either painstakingly type in deep.websystemdatalab.net or Google DPSDL and get through the link to the Jupyter Hub. And once you get there, there are 2 servers available, and obviously the one to choose is the BiDS'23 basic. So once you're in, the pod starts up. We preheated some nodes before the presentation, so I think everyone should be able to get in fairly quickly. Or I guess not, since evidently the image isn't on the board yet. But what I could do is go back to the slide that I forgot and go through the introduction to the demo while that's loading. So once we're in, we're going to go through one of the DPSDL system contains already a number of example notebooks. We're just going to be going through one of those, which makes use of the land cover dataset that we just saw, and also uses a dynamic data store, the CCI, and gets snow cover from that. So yeah, land cover, vegetation, crop type, forests versus crops versus other things, and going through what this is meant to show off. Firstly, the ingestion of data sets, the 2 types, the pre-digested analysis-ready data set and the dynamic loaded-on-demand data set. Interactive exploration of that data within the notebook, then Xcube is going to regrid one data set onto the other. They're actually both in the same CRS, but they've got different resolutions, so this is going to enable us to put them into the same cube. Then we fuse the variables into a data set, and then we use Xcube's masking function to mask off a particular land cover type to concentrate our analysis on. And with a little bit of luck, oh, look at that. That's the one we wanted. So, hopefully someone has managed to reach the launcher. At this point, we want to scroll down and go to the applications catalog here. And this is where we find the example notebooks. Scrolling down here, there's quite a few. Most of them are very simple, sort of single purpose. This is how you do thing X. Regridding and masking is a little more sophisticated and interesting, and has a bit more of a story to tell. So when this opens up, you actually get a pre-run version of the notebook with the results included. At least they should be. As a sort of shop window, and then to pull that into your own environment, you hit execute notebook, and that gets copied into your own user storage. Now, in order, yes, and we support different environments here, so you can see up here. This one is using the DPSDL Xcube 112 environment. That should be pre-selected automatically anyway. I just wanted to show that there are others available. For instance, if you need GPUs for ML or whatever, or different software versions. So, I think the slide already gave the necessary intro, so we'll dive right in. First, the imports that you get in every Jupyter notebook, the libraries that we need. And so here's our first introduction to the Xcube data stores. They register themselves with this sort of central registry. And then you can just select a data store by name. So we actually have two CCI data stores because they now offer a SAR interface as well, and this one uses the ODP interface rather. And now we open the other store we're going to be using. And this is the DPSDL's own public data bucket. And this is just using our standard S3 store, and you just tell it which bucket you're pointing it at, and it goes and gets what you want. So we can list the contents of that. These will look familiar because these were the ones that were coming up in the available list in the viewer. And yeah, going back to what you asked about the format, the ones with this levels suffix are precisely these multi-level ZARs, which are essentially a collection of pre-pyramided ZARs at different resolutions. So now we start by opening up this multi-level data set from the bucket. Happens very quickly because we haven't actually loaded any data. So because we're actually going to be working with the base data here, we use this getDataset function, and this fetches the underlying data set. The requested pyramid resolution 0 is not downsampled at all, so this is the full resolution original data set. Now we do a similar thing here. So this is showing off the search functionality of the CCI store. So here we can use some attributes, and we're searching here by essential climate variable, anything related to snow. Takes a little while to iterate through it, especially if we're all hitting that store at the same time. And you can see, I'm not sure which one, I think that might even be the one we're interested in. But as you see, we get a nice little data structure here containing 10 items with the full details of what they are, where they are, time range, space range, resolutions, and so forth. And so we pick that one, mode is Terra 2. Yeah, it was that one. And then we open this data set and ignore the warnings that come up. And what does the data set look like? here we have this sort of basic interactive exploratory display. It's latitude, longitude. It's in BiDS'23 and it's got these data variables, snow cover something, I forget what, but snow cover something, which is the variable we're going to be interested in, but also of interest the resolution and the size, which is not going to match up. Oh yes, also of note, it's pretty huge in every dimension. So as we can see, even though we've opened it, none of the data's been read because we haven't actually needed any of it yet. This is all fetched and processed on the fly as we come to it. Now, because that's rather huge, we take a smallish subset of it, going from January to the end of December 2015. And this geographical area, which is the edge of the Gulf of Bothnia that I showed in the viewer just now. And then we just use this standard X-array cell function here. And an X-cube is basically an X-array with a lot more facilities grafted on top of it. So anyone who's familiar with X-array, that all is part of X-cube anyway. And now we have our cut down land cover of slightly more sensible dimensions for a live demo. And then we do a similar thing with the snow cover. For snow cover, we're just looking at the month of April in 2015, but we're using the same bounding box. Now we look at the snow cover data set, and we are not quite ready to apply the mask, because as we see, we now have 1,000 by 1,000 resolution for snow cover versus 3,600 square for the land cover, which of course is the excuse to demonstrate X-cube's resampling. So we tell X-cube, this is an X-cube function rather than an X-array one that we imported at the start. We determine the grid mapping of the source data set. And as we can see here, we have the bounding box that we told it, resolution 0.01 degrees, and WGS84 for those who read fluent, WKT. And now we get the target grid mapping in the same way from the land cover. Target in the sense that this is what we're going to be transforming the source one onto. And if we look at this one, we see, as expected, that the resolution is significantly different. The CRS is denoted differently, but is actually the same, but it works just as well for converting between CRSs if you've got a UTM or a European LAEA or whatever. That's easy to regrid. And now we run the nub of the whole thing, which is resample in space, and this grinds along a little bit because now it's actually doing the... Now it finally actually has to work with some real data instead of just keeping it in the cloud and pretending it's there.
Is that using Dask in the background?
It could be if it's not, which is to say, you know, if you, I think this notebook doesn't have it, but making your notebook use Dask if the function is Dask capable, which it is just starting a Dask client at the start.
So where's this running now?
So this is running on an EOX server now, and if you just started a local Dask client, that might be more efficient because it's being handled by Dask. But there is also the option to spin up a dynamic multi-core Dask cluster for handling heavier workloads. I have to say in the rehearsal this went a little bit faster, but that's live demos for you. Oh, sorry. Too polite.
Does one can one change the resampling algorithm, or which one is used by default?
At the moment, No, I think you can you can change some parameters of it, but I think the fundamental algorithm is, at the moment, there's only one available. Yes?
Maybe another question while we waited. The dataset list that we were looking at the beginning. So we could also access these from a different notebook, right?
Yes.
There's not any subscription now that is going on in the background or something like they're completely openly available.
Yeah, as far as I know, as far as I know, the datasets in that list are not even they're not even restricted to DPSDL. It's actually a public bucket, which as long as the whole world doesn't discover it and hammer it at the same time and hit us for the download costs, then it'll probably stay that way for a while. It's it simplifies so many things, but you always have that knowledge at the back of your mind that someone could have used that. Okay, so it's finished. Thank you for the questions. So now we look at the original, this is just looking at the same grid mappings that we had, so I'll quickly flitch through that. Now we take a look at the resampled CRS, or rather a grid mapping generated from that one. And we see that now after the resampling, for some reason it's not showing the resolution. But just trust me, it's the same resolution, otherwise the next step wouldn't work.
Because you only inspect the CRS.
Oh, it's true, yes. Let's look at the whole grid mapping. Don't know what for this notebook. Let's see, yes. Thank you, I'm having my own notebook debugged live in front of me. Yeah, so we see we now have the resolution that we were interested in. And the number of pixels, horizontal and vertical, that we were interested in. So, now we play around a little bit with Xcube's masking facilities. So it's these in the data set, these are the standard CF conventions, methods of denoting flag values and providing that metadata in the attributes. And provided that the source data set is CF convention compliant in that aspect, Xcube can make use of that to pull out the values and the definitions of the mask values. In this case, it's land cover classes, of course. So here we have this nice table of different land covers and the numbers that denote them. And this is the one we're going to be playing with, cropland rain-fed herbaceous cover, of which apparently there's quite a lot around the Gulf of Bothnia. This was actually a slight diversion because it turns out that since Xcube knows all this anyway, it's clever enough to feed that straight in as a value in the mask object, so we can just, as long as we know what it's called, we can reference it by name, and we now have a mask. This is I won't talk too much about this because it's a slightly nasty hack in that it's the sort of floating point rounding error thing where the regridded data is essentially at the same values, but it's off by one sort of IEEE minimum 10 to the minus 19 or something. So in order to get the masking to go, we rather rudely copy across the latitude and longitude coordinates from one data set to the other, which are already virtually the same, but it's just that tiny difference that breaks the masking. There is a better solution for that. We just didn't have time to implement it in this notebook. So now we look at the mask. And here it is with the expected 3,600 by 3,600 and one data variable, and all that data variable is there for is to tell us whether or not that particular cell is rain-fed cropland. And now we can finally use this. We just pull this variable out. This is a standard X-array feature again. Pull that variable out of one data set and stick it in the other one, and it's just more convenient if we have the mask variable and the actual data variable of interest in the same data set, which is the resampled snow cover data set. So now coming down here and looking at the data variables, we have the mask, we have the snow cover fraction ground maybe? I don't know, CGF, snow cover something. Now let's take a look at this map. I apologize in advance for the color scheme. And here we can see, roughly as you'd expect, there's a bit more rain-fed cropland in the south than in the north. Not much cropland in the Arctic Circle, and quite a lot around the west coast of Finland. This here is the Gulf of Bothnia, because it's sort of squashed, equirectangular flat carré projection. It's all very vertically squashed down. Now, let's apply that mask. And this is just, again, a standard X-array function. Snow cover where the resampled snow cover is less than 100. I should explain, this is a sort of interesting little quirk of the data set. The way it comes from the provider is that invalid values are represented as values over 100. So this is essentially saying take anywhere where there's a valid value, and where crop mask is 1, which is to say where it is of the crop type that we were interested in. And there we have the output array, again keeping the same dimensions, and we've got the whole month of April in there, minus 1 day for some reason. Okay, so let's take a look. Take the first day, time equals 0, so that's just indexing or reducing in the terminology.
Now it's actually loading, right?
Now, yeah, exactly. So now it's actually pulling it out. Unfortunately, since we've cut down rather, that happens rather quickly. Oh, this is the color scheme I actually wanted to apologize for, because it's yellow on white, which is, I'm not a UX expert, but that's probably not optimal. There we go. Yep, so we can see here snow cover fraction. Again, it's more or less what you'd intuitively expect. The further north you go, there are yellow dots here for those sitting at the back. We have 100% snow cover up here, and we have, well, let's say around 100 here and around 0 there. And the further north you get, the more it snows, which I think sounds plausible. I think that's just the same thing plotting again. Copy paste over, I guess. So, fine, demonstrated reproducibility. Just to have some more fun with this, we'll now plot a histogram of the snow cover values within our masked cropland. And it's an interesting result. Fortunately, I don't have to pretend to be a scientist here, so I don't have to prove why that is. I think looking at that, it's super bimodal, and I just think, well, cropland, it tends to be very flat and not very variegated and very uniform, so I guess if snow stays lying on one bit of your field, then it's probably all over the field, as opposed to, you know, fields with rocks and trees and other crop-unfriendly things in them. And now, just as the anticlimactic finale, we plot the whole thing without the mask to see what the whole data set looks like. And now we can see snow cover not restricted to cropland, and it's very much the same kind of pattern, looking bimodal as we already saw in the histogram, and snowy up north and not so much down south. And that was almost on time, I think. Thank you.
I was wondering, should we continue without a break? I think we're good now. Yeah. Okay, and then we can finish a little earlier and we can discuss. So we'll take the next part on an OpenEO platform and the concept of user-defined processes. It's kind of new, at least for me, and I think it has been theoretically available, but it's only been functioning for a few weeks or months now. So we developed this notebook here, this example with Matthias and other colleagues. And I don't want to go much into OpenEO because you've probably heard it all over the tutorial Monday today already, and most of you are also familiar with the OpenEO basic concepts. But we did build OpenEO platform on top of the OpenEO API. You might know that story, and this docs section provides you quite good overview of the different resources. So there is the OpenEO API. We'll see some JSON encoding of that in a moment, and then you have the client libraries in Python, JavaScript, and R. And well, this is a great page for resources, also linking back to things that happened in the Horizon 2020 project, and so forth. So for those of you who are still at 5 o'clock able and willing to follow along, we had sent these instructions down here on how to sign up for a 30-day trial for OpenEO platform. It's at times a little tricky, but the procedure has already been simplified greatly. Sometimes people still get lost. We do have some vouchers here right now that allow you to follow along without going through this 30-day trial period. Did anyone succeed in doing that? I mean, we sent an email out for registering for the 30-day trial. No one. So if anyone wants to, James failed. We don't want to talk about that.
No, I got it working on one account.
Okay, good.
It's just that I've had so many free 30-day
Yeah,
trials.
yeah, exactly. Yeah.
I guess that's part of the mechanism.
So it's not that difficult. It has been simplified quite a bit now, and so the process starts here. I'm not going to go through that right now, but then it uses basically, you can use OpenID Connect using different identity providers to log in. So it's actually a very nice feature. Also, maybe for you, to keep to bring you up to date here, so the OpenEO platform is actually running on 3 different backends. So we have EODC. We have Terrascope, we have Sentinel Hub, and there is also an interface to EuroDataCube and the EuroDataCube Xcube and EuroDataCube GeoDB to a certain extent. So that's kind of the federated backends behind OpenEO platform. So, okay, you can, we're going to use this lab openeo.cloud, so you can try that. So anyone who wants to follow along can just call up this lab environment. So that's lab openeo.cloud. And we do then have these magic paper vouchers, like in an old Monopoly game or so, that we can give to you. And then you actually get a... Yeah. And I think if I start a private window, and I pretend I know of nothing, and then I call lab openeo.cloud. So you're going to have to call select OpenEO platform on this screen, and that takes you then to the sign in. And here, this is the EGI check-in. And if you select here EGI single sign-on, right, Matthias? Yeah. EGI single sign-on, you get to this screen, and there you can put in the username and the passwords that we just handed out on paper. And that should allow you to follow along with the Jupyter Lab. Excellent. So and before we get started, maybe, I'll put up this again. So there is a GitHub repository called OpenEO Community Examples. And there we have the notebook that we're going to play through now. That's sentinel1_stats.notebook. There's also this QR code if it helps anyone to find it quicker. Otherwise, I think if you Google for OpenEO Community Examples.
It's also in the lab, right?
Is it pre-configured?
I think so, yeah.
Not on mine. I don't think so.
Not in your
Community examples. Oh, yeah. Python.
Python.
Oh, yeah, it is there. Excellent.
It's there.
Oh, nice.
Because I think the link doesn't work anymore after the
Yeah, exactly. Oh, hang on. This is 2 days old.
Yeah, you need to back. The new accounts have the newer version.
Yeah, exactly.
So it's
Yeah. Yeah. So I'll use this one here. Exactly. Okay, so before we get started with the notebook, maybe just really quick that OpenEO users, OpenEO platform users can use the Jupyter Lab environment where they can work in the Python client library, what we're doing here. They can also use the OpenEO R client or the JavaScript client to code workflows. But a second important interface for OpenEO is the web editor. And the web editor looks something like this, and we're going to switch back and forth between Jupyter Lab environment and the web editor in this tutorial. So in the web editor, you find, for example, the overview of the different collections. So in OpenEO platform, that's 138 collections. You can, you can click on the different collections. You get the metadata. You get the extent. You see which provider, which backend is actually providing this data set. And then the web editor has this graphical workflow builder where you can create a workflow by just putting together these graphical boxes of inputs and processes. So these are the OpenEO processes that are defined by the API and that can then be reused here. And you can combine processes with the outputs and everything, and we'll take a look at that later again. But now we switch to this notebook that we're going to play through. So the idea was to take a very simple workflow to aggregate a time series of Sentinel-1 data into a set of statistical metrics. So something that people often use in machine learning inference workflows also. So a quite useful example. That's not an NDVI example. Nope. And so we're going to go through this. I'm going to start here by importing the OpenEO library and a couple of specific OpenEO processes and the Xarray, Matplotlib, and libraries and the utils library. So there's a little file called utils.py that has a couple of widgets that we can use in this example here. We're going to load that as well. That step here might create a couple of issues in your case if the Jupyter Lab is not pre-configured properly, so let us know if anyone has any issues here. Then we can slow down a bit. And then we continue this example. We have a couple of plotting parameters here that we can just execute this cell. And then this is where the magic starts happening. So this is OpenEO.connect. So we're connecting to the OpenEO.cloud backend, and we're using the OpenID Connect authentication mechanism. So here, in my case, as I was already logged in, it's using this refresh token for the authentication. Otherwise, you are taken to this EGI login screen where you can use a identity provider of your choice to identify yourself. Does that work for those who are following along?
It worked for me.
Great. Okay, and so the first block in this notebook is just working with the Sentinel-1 GRD Sigma 0 collection, and we're just going to extract a data cube that we're then going to aggregate into these statistical metrics. So the first step here is a kind of a convenience functionality that spins up a little widget here where you can select the area of interest. So the Sentinel-1 GRD Sigma 0 collection is a global collection. It's the global Sentinel-1 collection. And for the sake of this tutorial, I'm going to select a very small area. So you have a a little widget, AOI selection widget here, and I'm just going to select this little area here. This should work fairly quickly, and then we execute the next cell. We extract the bounding box coordinates. We pass these bounding box coordinates into the spatial extent variable. And then this is now an important step here. Can you guys see this? Yes. Okay. So this is then the load collection step. And for all of you who know OpenEO and who've worked with Google Earth Engine, this is nothing new. For the others, this is kind of already an essential abstraction step, because we're no longer working on the basis of files and file paths, but we're working on the basis of collections, which abstract all of the file formats, file sizes, and also the projection of the data underneath. So we're loading the collection, Sentinel-1 GRD, with the temporal and spatial extent that we have defined above, and the two bands, the polarization, vertical horizontal and vertical. So we can execute this, nothing happens. It just basically creates this data cube, virtual data cube object called S1 raw in this case, that we're going to use for further down in this example. So the first thing we're going to do is just to download this data cube that we have just created, and we're going to do that with synchronous execution. So in OpenEO, OpenEO platform, you can execute processes either synchronously or asynchronously as batch jobs. And this is an example where we do it through synchronous execution, and it's also a fairly small extent. So for the temporal extent, we're using here May and June of 2023. And it's a fairly small spatial extent, so this should take about a minute to download using this synchronous execution. And we're going to take that time and enjoy the silence. Anyone following along? Problems? First row.
Can we see the process graph?
Yeah, in a minute. For synchronous execution, the process graph will not be shown in the editor, but we're going to do a batch jobs execution in a minute, and then we see the process graph as defined in JSON. Yeah. So there's also in this notebook, Vito colleagues here put the documentation section in here for the batch job. So it's all explained here quite in detail, how batch jobs are created, how batch jobs are executed, and how you can monitor their progress. But for small jobs like this, just downloading a small data cube, synchronous execution is just fine, and it's actually nice how it's also executed just in this one-liner. So I think it should, the file is here. So we're downloading this also as netcdf. I'm not a big fan, but it works still the best. No, it's still the file format that works somehow the most, especially across many time steps.
Is it the only option?
No, GeoTIFF also works, but if you have many time steps, the netcdf tends to work better in OpenEO. I also prefer the GeoTIFF. If you go to the editor, you can actually, I think, see the different output formats, no? Export file formats, so we have GeoTIFF. You can also create, PNGs or SAR. I haven't used SAR in OpenEO much, but
Either.
no.
Rather new.
So it took 2 minutes and 50 seconds, a bit longer than in the previous test, no?
Yeah, the tutorial is using resources, I guess.
Sorry?
The tutorial is using the
I guess
resources.
so. Okay, so we have the netcdf file downloaded to our Jupyter Lab workspace here. And we can then simply open this with X-ray. We see the dimensions here, 1400 by 600 and 10 temporal dimensions. We can then also plot the time values, so the time steps here, and we see between May and end of June, we had about 10 observations from Sentinel-1. And we can then do here a simple plot of the last time step in this time series. So that's just an example on how to access the data and how to export a data cube in OpenEO platform. Next, we want to transform this time series of Sentinel-1 observations, so this data cube of 10 backscatter values to statistical metrics, right? And what we typically use is the percentile values of the distribution over time of the backscatter values, or the median, or the minimum and maximum. And that's what we're doing here in this function. So we have a function called getStats, and it combines a couple of OpenEO processes here. On the one hand, it has an array create, where it combines the minimum, max, mean, and standard deviation of the data array that we're passing into the function, so of our data cube here. And then also we're calculating some quantile statistics, so the 10th, 50th, and 90th percent quantile. And then we use another OpenEO process called array concatenate, or array concat, to merge these two arrays together into, and then return one resulting array. So that's all standard Python stuff using OpenEO functions. However, they're using also this process builder object, and I have to say that's a little bit beyond my OpenEO expertise, so I pass over to Matthias to explain the process builder concept.
So the OpenEO Python client that is running here has basically a way to create a graph that is sent to the backend in the end, to the server that is executed. And this graph is generated by different calls here. And for example, the getStats method is passed to a function that is called on each individual time series. Right? And this function is basically one level down, right? So the first level is you load the data, you apply something on the data cube, and that is directly executed on the connection, which is also a process builder internally. It builds this JSON graph. But then down the line, of course, in this function is also called, you have another graph that is generated. And this is what it is, right? It's just an object that gives you all the OpenEO processes to work on in this context, then generates the whole process graph. So that's just an internal thing to generate the JSON, basically. To have access to the processes in OpenEO in this Python function.
So if we were just to use a single OpenEO process in this function, we would not need the process builder. No.
Okay. Just pass min or max.
Mm-hmm. Okay, we'll show an alternative solution to defining this function a little bit further down. Process builder is also documented, but we don't have to spend too much time here. So anyway, the function itself is pretty clear, as we have just walked through it. And then in this example, we run this a little bit differently. We use apply dimension, which is another OpenEO process, calling the getStats function that we have just defined, and applying it over the temporal dimension and targeting the bands where this is added. The second step here then basically performs a rename of the bands, so that we have VV min, VV max, and so forth later on. So now we're gonna we had the synchronous execution of the job in the previous example. So now we're gonna use the batch job execution for creating this first set of statistical metrics on our data cube that we had defined earlier. So we send this off with execute batch. We define a title for the batch job, and we define a file name for the output netcdf file that we're creating. And now we're going to switch to the editor. We're logged in here. We can, in the job monitoring, we can refresh. This one is old. We can refresh and we see that the batch job has been created. So Sentinel-1 GRD statistics is now in the batch job monitoring tab here. And it would have been automatically queued. And we see in the Jupyter lab that the job is now queued. It's going to periodically check the status of the process. And at the same time, we can monitor it also in the editor. And now here's some nice features on the process graph. So we can, here in the editor, we can click on this edit process button, and we see the graphical overall workflow of this process, where you have the inputs, the Sentinel-1 Sigma-0 collection, the apply dimension step, the renaming of the bands, and saving of the results as netcdf. This is the graphical view, and it doesn't help you much, but the nice duality here is that you can switch down here to the JSON encoding of the process graph. So this is really the OpenEO API-based encoding of the process graph that already allows you to share this process basically with different backends that support OpenEO. So I could send this now to our colleagues here from Telespazio Vega or so of EOX, and they could execute this in their backends. No? So this is already a first nice aspect in terms of reproducibility and replicability, that the JSON encoding of the process graph is basically, it can be reused in other places. There's another nice feature of the editor that I wanted to highlight, and that is as the process graph is encoded in JSON, and the client libraries also follow this API encoded in JSON, we can basically use this function to automatically translate it between the different programming languages. So this is now the JavaScript definition of the workflow, the Python definition of the workflow, and the R definition of the workflow, which is a very nice feature for capacity building, and also if you come from a different programming language and you're not so familiar with one or the other. Okay, so the process is still queued. Classic. So we have prepared already in the meantime the result. Should we use them? Yes, of course.
How is the status of queue? So what we are waiting for?
What are we waiting for? We're waiting for the batch job to...
I mean, yeah,
sorry.
what exactly are we waiting? Because what other jobs are in the queue? So that kind of information is available?
No, not for us. That's, well, no. I don't think as a standard OpenEO platform user you will see the queue of the Veto backend in this case.
Can be nice to know, and just as a feedback, I mean, maybe it can be nice to know what's our location in the queue. Like,
At least the number of...
Yeah.
Yeah.
Yeah. Okay, I think I'm just gonna, what are we creating here? STJD stats. Let me just move this one here. Okay, I'm gonna pretend this job has completed. It hasn't, but you know, just for the sake of the time, it's 5:30. So we have another text block in here that I won't be able to execute right now, I don't believe. It shows you how you can extract the signed URL of this job result that you can then paste directly into QGIS. It's actually quite a nice feature. I don't think I have it in the clipboard anymore, no. But we're going to skip this step. So we should be able to now look at the Xcube properties, Xarray properties of the result file that should come out of this batch job. Funny, it's still queued. Earlier it went quite quick. Okay. It's not going to complete before this is completed, no? Okay, maybe we move to the best part now. So for the UDP, okay, because I don't know, the queue is not moving much here. So let's look at this user-defined process concept. So did it finish? No. So user-defined process is a way in OpenEO to share mature workflows with other users and make them available for reuse. So what we do here is, yeah, this is not going to complete before I. Yeah. So the first step to define a UDP is basically to define the parameters that we want to make parameterizable by the user. So that we have two parameters in this case. We have the temporal extent of our data cube and the spatial extent of our data cube. And we define both of these as parameters here. And then we define the rest of our processing graph. So again, we have the load collection step where we load the Sentinel-1 data with the temporal and spatial extent from the parameters that we have just defined. And then there's a much more compact way of describing, implementing this metric calculation. So we run this on the Sentinel-1 raw data cube. We use the apply dimension process. And we have a lambda function here basically that does array concatenate with the first array containing the min, max, mean, and standard deviation, and the second array containing the quantiles, again, 10, 50, and 90%. And we run this on the temporal dimension and target as bands. And then we have the same step that we had earlier with the renaming of the band names here. And now we have this process here, save user-defined process. This is actually the step where you define this as a user-defined process. It won't execute because the queue up there. No. So in this case, we have the whole process graph that we have defined in these two cells here. We have now defined as a user-defined process. We call it S1 stats. And we pass the parameters and a summary and a description. And we have a flag there, public true, that other people can basically reuse it and find it. And once you do that, yeah, okay.
Maybe stop the block with the batch job.
Yeah.
The others should execute.
Exactly. So now, as soon as we did this save user-defined process as a user-defined function called S1 stats, we can go back to the editor and, sorry? It just,
Job just finished.
yeah,
Anyway.
great. Where's the refresh button? Yeah, sorry, exactly. So now we have the S1 stats user-defined process here in the custom processes tab. So we can basically call the process graph at any point. We have, you see here that the parameters are in the process graph. And this process is now also in the list of OpenEO processes. So if we scroll down here to S1 stats, users can basically now reuse this as a predefined process that they can now integrate into larger workflows where they can add other processes and make these part of a larger workflow, which is a very nice property. So how can you now use this UDP that we have just defined to run this process on a data cube? There are, again, a couple of specific processes to do that. So one is data cube from process. Here we call the Sentinel-1 stats UDP that we have just created. We don't have I don't know if we need this really. So we might want to pass in this public URL. We're still not completely sure if we need it, but it's better to be safe. And then we pass in the parameters temporal extent and spatial extent, and we can execute this user-defined process. Again here, doing it synchronously. So we executed this again synchronously. I think this one should really not take that long. Let's see with the queue if it's a little different. But let us know if you have any questions. So I think it's a really nice way of enabling reuse of mature workflows. So maybe again here we had the standard processing graph of the metrics calculation, of the statistics calculation. And then we transformed that basically into a reusable user-defined process that is now appears now under the custom processes, and that can be reused, and we can even use it in larger workflows now by pulling it in as a single block in the graphical process builder. Let's see what this this is still working. Okay.
Sorry, may I ask a question?
Of course.
So for this synchronous processing,
Mm-hmm.
it is still done by the backend, right?
Yes.
So basically, you are still sending it to the queue, and it is processed within the queue. Right?
There are two queues, one for synchronous and one for batch
Mm-hmm.
jobs.
Mm-hmm.
And there are two different queues.
Mhm.
I mean, that is a specific of the implementation, right? The
Yeah.
server might be different on other implementations. Not sure how it's at UDC, but at Vito it's the way that there are two different queues for synchronous and batch jobs.
Mm-hmm.
We should stop the other tutorial. It's really
Which one's going on? The Pangeo one. Oh.
But it's finished.
It's finished. Okay. So now, very good. So the file has been downloaded. SAR UDP. That's the file that we have just downloaded, and we can look at the X-ray dimension of this. So yeah, and there's. Let me see. We can also do a plot of this exactly. So we have the VV mean and the VH mean here plotted, and yeah, we could also download this and bring this into QGIS if you wanted, or through the signed URLs that we have shown earlier. 500 kilobytes, that's tiny. Okay. So, and then there are another couple of tricks on how this user-defined process can be used in the editor. I think we have inserted it here into the notebook so that you can kind of follow this later on also. But I think the one thing that we wanted to show is that the stats, S1 stats, can also be found by simply searching in the process directory in the editor.
Is this
And the-
findable for everybody now?
Yeah, no, not yet, not yet. You need to use this this URL that we have generated here. So if I shared this URL with you, then you can call the process like we have done it here, right, with the public URL. Then you can reuse it. But I mean, that's where it should go, that anyone can discover the processes and reuse them without this additional stuff, no? So there's another nice feature, and which is the OpenEO wizard functionality that Matthias has developed here. So the wizard allows you to execute OpenEO workflows without any interactions with code. And there is now a wizard functionality called Run UDP, where you find the UDP that you have just defined or selected. You can select it, and you can basically walk through this wizard functionality. You can set your AOI, your area, your temporal frame of interest, and you can then execute it as a batch job, synchronous processing, or just queue it for later. And this allows also, people who are really not familiar with coding to run OpenEO processes or your UDP in a way that they don't have to interact with the Jupyter Notebook or a graphical workflow builder. So that's a very nice additional feature. And you can even generate a URL like this with your UDP wizard, Matthias, no? And then the process S1 stats. And you can click on it and you authenticate with your OpenID Connect, and you are directly taken to this wizard, which allows you to run this with the default parameters here. Yeah, and we could now queue this as an additional batch job. There we go. Let's see if this one finishes. So I think this is basically what we wanted to show. Any questions or comments? Otherwise, we invite you to explore this notebook maybe. It's in the OpenEO community examples, Sentinel 1 stats. And yeah, I think this UDP concept has really great properties for reuse of mature workflows, for sharing mature workflows. And maybe also as a last point here, OpenEO is also part of the ESA network of resources. So ESA will sponsor any pre-commercial usage of OpenEO. So go to the network of resources and get an annual license or a research group license and explore this platform and its services. Yeah, we'll stop here.
So what I'm going to talk is really how the OREO application package served the objectives of being open and reproducibility workflows. Thanks. Okay. Oops, next one. We started the application package drivers or the objectives why we were thinking about it and we are developing this is really to decouple the application development from the application, the exploitation platforms operators, so that there is no locked in the sense you are not obliged to go to a specific platform provider, you're not obliged to go to a specific backend to really develop an application. So you're really focusing on your application that is running in your computer, in your own environments, and you minimize the specific platform-specific particularities. Important here is really to think, was a main driver, is to think in terms that your application be compatible with different and several execution scenarios. Something that is running locally should run in your private cluster, should run in your Kubernetes, or should run into a platform. And how to do this? Without bigger change, how can we do that exploitation platforms can support this type of application and your application serves different execution scenarios. Just to the next one, and then so we've been working this in several test beds, activities in the OGC from the 13, 14, 16. Lots of people here worked together on this in different. There was, if you go to the documents, it's funny, but to see that okay, in 13 we went to one way, and then in 14 we changed to another one. So we're really evolving. And also in terms of agreements, because there is different organizations, there were different persons, different options from different platform owners, and we're trying to have a consensus and to define a best practice where we could define what is an application package and how you provide the metadata and how you do it in such a way that is not dependent on your backend, but is transportable. Just next one. And so we did this best practice a few years ago. Lots of institutions present here also do submitting. Here the idea at the time was really focusing in three main viewpoints. In a sense, you are a developer, how do you build your application? You are an integrator, how do you package that application? As in a platform, what you need to do to be able to deploy and to exploit this type. Then, I will not go into the details here, the CWL and so on that we were in the previous meeting. We have this material, and if you're interested, just pass by your booth. But really, we have a way and metadata that define a standard way to define parameters, software items, executable dependencies. So what is your environment that you need to run, your containers, your libraries, all those things are specified. And really supporting or your development or even a machine-to-machine execution scenarios. Because with this, what you are able to do is running something locally, but also running as a service inside of a platform. What it means running as a service. Then you do actual algorithm hosting. You have that application, you can put it on the server, can do algorithm hosting, and then you can have a cost model applied to it. So it's really the full life cycle of the application development. And then I promise this is the last one. Reproducible open science. This is the three main points for us that are important and what we need to really agree in a sense how the application package is supporting this. For one side is reusability, the other is portability, and the other is transparency. And what we mean about reusability is that I've made something in an article or a paper, I want you to try it out. Try it out in your local computer or in a platform or somewhere else. Portability, so we enter here. In a sense, that's really important that you develop algorithms and workflows that are able to run in different environments without you scratching your head and how to do it. And then transparency. In the end, what we want is to have a GitHub, open source code, if possible, available, and we can download it, we can remove that information and run it where we want to do it. And with this in mind, I think it's my last slide. Okay, no, it's not few. Here is a few information that you need. For example, if you do the application package and you want to run it local, what are the tools? What are the open source tools that you need? So it's quite, if you have a local execution or Kubernetes or HPC cluster or HCI process, you have different open source components that help you out in doing this. And then just another one with links also, but okay, is the this is using Stack, this is using lots of stuff that I'm not going to the details. Now Fabrice, what is going to show you, and you have the links, you can try it, you have the username and password yourself. It's a notebook where you are really doing reproducibility of an application. Someone developed an application, informed you that that application is available, and now you want to try it out. And I'll leave this to you.
Okay, I don't need it. Okay, so thank you, Pedro, for the introduction. Well, we have actually created a scenario, and this is as an answer to Claudia's request to provide evidence that the application package is a good strategy to ensure reproducibility. And we have created a small story scenario. So we have two actors, two personas. Alice, who developed a water body detection Earth observation application package. And Bob, that wants to reproduce and reuse that output. So the scenario is that Alice included in the water body detection application package a continuous regression step that relied on GitHub Actions to build the containers, push the build containers to GitHub container registry, update the application package with container references, and push the updated application package to GitHub Artifact registry. Well, this doesn't mean anything to you, I'm sure, but still, let's see. Bob gets an email from Alice detecting water bodies with NDWI and the OTSU threshold. Okay, hi Bob, check out my new application package. And here's the link. So the Git repo, we can open it here. And what did Alice do? Actually, she left the application packages. So what Pedro was mentioning is, this is a CWL workflow. CWL is an open standard for describing command line tools and workflows, how these are orchestrated. It's a standard that comes from the bioinformatics community, but that's since evolved in the last 10 to 15 years. So being an open standard, you're also invited to participate in discussions, evolutions of the standard. So it's definitely an open process around this specification. So actually what it does, it changes Python applications within containers. So you see containers here. And when Alice mentioned the release, she actually provided 3 application packages in her release 1.0. And this is what Bob expects to get as an input for his reproducibility scenario. So we have a small notebook demonstrating the functionalities. So a few imports that we will need. So nothing too fancy. PyStack, raster.io, CWL tool. This will be our CWL runner. This is an environment in the cloud hosted by Jupyter Hub, and this is Visual Studio in the cloud. The small difference is that we have a container engine, and we check if this notebook has Podman or a Docker. In our case, we have Podman. Podman is definitely an equivalent of Docker, actually developed earlier by Red Hat. And the first thing that we do, we interact with the release, and we see what assets, programmatically, what assets Alice actually exposed. I don't know why, but there's some bug in this GitHub API. It takes 10 seconds to do this. Fine. So we see you can recognize the three application package URLs. We have just added a few information. We have read the title of the application package, and we have read the doc, which is the small abstract provided, and we have parsed it already. This is just to support what we do. So we have just read 3 YAML files, URLs, and read those YAML files with the CWL utility parser, so that we have all the elements that we want. Then Bob carries on. So I've mistakenly created the request again. Sorry for that. I've been parser. So Bob decides to use the first application package. So we get it like this. And reading a commodity class to read the parameters of this application. So we use a bounding box provided as a string. We provide an array of bands that we have to use for our application package. An EPSG code describing the code that is used for defining the area of interest, so that the steps know how to do, and the list of stack items that we want to process. And this is what is described here. So for sake of reproducibility, we're going to tackle on the Earth Search Stack API catalog. So we use the PyStack client library to establish a connection to the Stack API endpoint. We do a small query on the start time and end time and bounding box, cloud cover minus lower than 5, and that will provide us a pair of acquisitions over this area. So we see that we have a few water bodies that this kind of application can detect. So the application package wanted us to use stack items. This is what we are going to provide as input data to our execution. We use the commodity class and model to create this dictionary. So those are actually the parameters that we will use for our processing. So this is the area of interest, the same as used for our research on the stack catalog. We will use the green and near to derive the NDWI water index, and use the PSG code supporting this, and those are the stack items that we will process. Okay, so this dictionary gets serialized in a small file that we have here, nothing too fancy. AOI bands, EPSG code stack items as before. And now we will use CWL tools. So we have imported this main method from the CWL tool. We say, well, we want to use Podman as the container engine. We want to use parallel processing to speed up things. And let's have the application package being executed. So what you see is that CWL runner is just running each of the steps with Podman and providing the parameters for each of the steps. We have actually 4 steps in our workflow. First, we crop the near, then the green band, and then we use the normalized difference and apply the Otsu step, and finally do the generation of the stack catalog. So in the end, what happens, CWL tool doesn't do any magic. It reads the CWL document, launches the containers, builds the command line tools, mounts all the volumes between all the different steps so that you don't have to bother about everything. So you see, if we look at one, actually the node stack of our workflow uses Podman, mounted all the volumes that it needed. So you see, we don't have to really be bothered by anything. A CWL runner has to, by specification, do this. So we have a dictionary with the results that were generated by this application package. So it is a listing of what we have on the file system. We said, well, generate this. But the nice thing about this is that the best practice
includes a practice that your results must be described as a stack catalog. So it is actually what we have as the output, and what we have generated with what our two inputs were two water bodies detected. So Bob uses a stack Python library to open the first stack item. This is a typical stack manipulation. We inspect the data asset, and this is one of the results that we have. This is exactly one of those files here that we have. And Bob looks at that results, uses raster IO to filter and apply the sieve algorithm and plot that on a map to see whether Alice's application package actually is delivering the results that she is suggesting it does. So let it apply that. I guess the tool was faster at processing this than displaying the results. Well, this is what the algorithm actually detected. So you see. And finally, to close our user scenario, Bob says to Alice, the results look promising. So the takeaway messages is that CWL, by being an open standard, does not limit you to a certain implementation of that. You have different implementations, as we have seen in the slide. So we have CWL tool for local execution, Calrissian for running CWL in the cloud, on Kubernetes. In the cloud doesn't mean anything, sorry. Running this same application on HPC with Toil or Streamflow or Arvados. And also you can deploy this application package as it is on the Zoo OGC API process implementation and have it exposed as a processing service, as a web service. We advocate that the input manifest and output manifest for data is stack, because it definitely provides an advantage over lousy, terrible approaches such as find me the file on the file system that ends with b01.tif. That is definitely a weak approach. So stack clearly fills the gap here, and we don't really care about what happens between the steps in the workflow. That could be TIFF, that could be whatever format that you have, but in the end, you need to produce a stack item. Well, that was fast, but it's 3 minutes ahead. Yes, I'm happy to take a few questions if you want.
Maybe I just want to add one thing on your presentation. Equally as presented by Patrick with OREO, we have now a number of services that are part of the NOR network of resources that are compliant with application package and can be sponsored. The services are at the level of the execution layer, so you can take your application package and execute it there, but are also services to help you preparing application packages and optimize it. Because the other element that was not shown, not because of time, is that building the application package also allow you to do that process we call cloudification of an application, because it is developed with the mindset of running over cloud platform, and therefore allow you to scale that application over that infrastructure. So that obviously requires some deep knowledge about what you're doing. It might be a bit too much to ask for scientists, but we then are now offering services along those lines in the network of resources.
Just to complement that, because this is the easiest sponsoring part, but the more commercial side. We as TerraDuer are also in revenue sharing agreements with developers. So it means that we are doing actual algorithm hosting, where we define with the developers, we define a cost model, a price model, and we enter into a revenue sharing model. We have already complex chains of interferometry, complex chains of algorithms, not your simple NDVI, with a little bit more. So this type of algorithms, we are interested also in this participation, not only for getting sponsoring from ESA, I think it's really great, but also going into a revenue sharing with developers, so that you are able to have a platform where you can host your application, host your algorithm, you have a guarantee that the data is there, you have a guarantee that your users are able to execute, and to obtain your results. This is more commercial side of it.
Okay.
No, but it's actually an interesting point because the other elements we at ESA try to address is how we move from a research environment towards an operational environment. And those kind of questions are the ones that rise because how you share the revenues, how you actually ensure the maintenance of that service. Because usually scientists don't want to do maintenance of an operational service, they don't really care about. So we do actually enter in these kind of problems, and we are kind of exploring them.
Okay. Well, one last word is that we have published a guide for the BiDS'23 mastering Earth observation application packaging with CWL, so it's an open resource on GitHub. Feel free to look at the inner details and how everything.
How this application, how
Yeah.
Alice made this application.
Yes, this is Alice's part, and
It's a core part because basically
What was our 1 hour 1 hour before we were.
do you have some tools to facilitate application development, or people
yes,
are
yes. And we have an online environment,
okay.
and if you pass by our booth, we can show you our booth. But yes, we have an environment, now with migration environment where you have this type of tools. Testing.
Yeah, I was just wondering where, where's actually the scientific workflow defined that is executed to delineate these water bodies? Is that a Python file that's called in
Yeah, yeah.
CWL, or?
no, it's Python. It's Python code. So the application is described here.
Can
So
you show us the point where it's actually in the
yeah.
the CWL file?
Yes, I can show you the Python code for the crop step. So it exposes a command line tool, and it is put in a container like this. And this is what the CWL builds. The CWL executes this container with each of the step is then a small command line tool step, where we say, environment variables, Docker, the base command, and how you want to map the inputs to the command line. Okay. Then the next step is to wrap that. Well, okay, this is the. So in the end, you have a block with the workflow that will define inputs, outputs, and the steps. And you see not crop will run crop. And this ID here is nothing less, nothing more than the command line tool that we had before. So all the orchestration happens in this section here, and it maps and the normalized difference will take the output from here, and we'll use it here, and then that's how CWL orchestrates things. So you always start with a command line tool, container, command line tool, wrapper, workflow, and you're done.
Is it always file-based? Sorry, between this, okay, you connect the different command lines.
Mm-hmm.
So how do you communicate
No,
output?
It could be an expression. You could use an expression, say value is 2, and you get this 2, and you to the next step. It's not always file driven between the steps. You could have a step that would produce a value,
Yeah.
not a file. 2, it's a value 2.
No, but I mean they are talking. Okay, 2 is a single value, but normally what we communicate is usually data sets, right?
Yeah.
So if it's a data set, then
Mhm.
it is file-based. Is this correct?
One important point probably also to quick question from Patrick is you could have
This is what you mean, yeah?
different one point you could different resources for the different nodes. You can specify that.
Ah, yeah.
This is a very important point. So you don't decide that not the full, you can say the whole workflow, but no, this node here really needs bigger RAM and bigger CPU.
This is more obvious when we run this. So we have an execution scenario on Kubernetes, and we use Calrissian. And what we can tell in the Kubernetes language is say assign this the pods So we saw that the CWL execution triggers a container, no? Calrissian will trigger a pod instead of a container. So this is why you get scalability. But the pods that this command line tool will trigger will go to a node selector that you define here. So if your application package has steps that are not too eager on the RAM, you could go to cheaper nodes with these node selectors. If you do snap and things like that, 32 gigabytes, 64, whatever, you can go to a node selector. And that provided with the auto scaling capacities of a Kubernetes cluster, you can scale from 0 nodes and only have the resources scale up when you have an execution like this to happen.
Really important point for the commercial side is that you have full traceability in the sense of what was the cost of each type of the node and which type of resources were used when you're doing batch processing. This is really, for us, really key also to find the cost model.
Yes, I think.
One question. So if you run a command in CWL and then you want to hand it over to another node, how is the storage handed over? Is this what you meant by the volumes you attach and reattach to certain containers, or?
But this is the CWL runner that takes care of that piping.
Okay.
You don't do anything else in CWL rather than actually where is that? That's saying that this normalized difference step will read the results of the node crop. And node crop is this one, okay, that actually has 2 instances because we scatter on the things. So it's the CWL specification defines how people write this, but also define how CWL runners must be implemented. So they provide the CWL runner must do this, 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 and that. And amongst the this and this and this and that, it will say if it's a directory, you mount it and things. So this is part of the standard. We lazily rely on implementations of runners. Okay.
How do you manage error conditions if something happens?
You have conditional behavior in your workflows. But typically CWL runners, when you get exit code 1 or whatever, it's execution is terminated. So you can do different scenarios. So if you say, if the file condition or value condition of your step is like this, then you go to this branch of execution or the another. But if an application exits with does not exit with 0, it's so for instance, this is, to pick up on what Pedro was saying, this is a JSON usage report of all the steps that we had. For instance, we had the node crop 9 consumed 3.5 megabytes RAM megabytes and this value of CPU hours. So in the end, you know what each of the steps have consumed in your Kubernetes cluster. But those are details about consumption of resources on the this is what would go to billing. This is usage transformed by, okay? We are here until Thursday. We have a booth. This is also part of Code Sprints. If you have ideas and you want to meet at the OGC, the OSGeo Code Sprint, we will be able to support that. Thank you.